I'm the first author here with Eric Brynjolfsson and Dan Schaller, former postdoc. This is the result of a little over 2-year field study with a firm that I'm going to call JointBot through a 3.5-year research program that's just wound down about AI-enabled robotic automation in the warehousing industry. There we go. In a slide, thanks to Abhishek Nagraj for this convention. In short, there's a lot of great literature that shows that it's very hard to build value-adding skill as a non-professional at work. And in fact, professionals are somewhat toxic to that process, which struck us as bonkers, particularly because we have a field site in which the opposite occurred. So it's, this field study is exploring the conditions under which non-professionals might actually build value-adding skill because of contact with professionals in complicated work. And the short answer, if you had to walk away now, is that we had a set of conditions that the literature would predict, if you look at the literature carefully, would enhance non-professional skills, which is a shared production task, not writing the ML code, but the end result, which is to say picking and moving goods. When that was shared with professionals and non-professionals had slack time, they solved problems, as humans are wont to do in work, that added value to the product itself, built tech, helped build the tech and their skill, and we have career outcomes data for those folks as well over a number of years. So this is just sort of substantiating the motivation, which is to say we have a massive problematic skills gap in the economy. Morgan Frank is here in the audience somewhere. There he is. So there's a number of folks, more than I, Sarah Bana is also here, who have done work that shows that in particular, there is a bundle of sort of sensory motor related skills that one can acquire, and it's very hard to move from that bundle of skills towards the sort of social and cognitive side, this barbell effect, and the transition is really, really difficult. But we need folks to make this transition. Prior research suggests that for those folks in that sensory motor sort of non-professional bundle, working with professionals seems caustic to making that journey, actually. At least findings around skill and studies focused on skill. That we have things like task segregation and rationalization and so on. And occupations tend to develop skill for their own and not for others. That's how they function. And we have a bunch of literature that suggests that technology is an accelerant to those negative dynamics. Basically, the de-skilling literature is relatively obvious, but we have these participative modes of design and development for technology that up close are still extractive and exploitative of the people whose expertise is being replicated through automation. And yeah, so we had data from the field that indicated, well, the opposite seems to be happening here, so that can't be totally right systematically. And in fact, if you look at the work on, the research on work involving technology, it is very evident that people who are non-professionals are seeing things and capable of doing things that are value-added in organizations that professionals literally cannot see in some cases. There are great studies that show that professionals are blind to certain classes of problems and so on. And the professionals, when accidentally, now the studies don't focus on skill development per se, but when professionals involve non-professionals in problems that stretch both of their capabilities, you get better results, but also it seems to indicate that you can build skill. I have myself a study published in ASQ in 2023 that shows that just by doing workarounds in work involving complex technology repetitively, you have to build skill to enact those reliably. That's a skill. This was with professionals, though, not with non-professionals. Steve Barley is the beginning and the end of much important work on skill and work and technology and so on. And he basically said in '88 that the work on de-skilling has looked in places where you would expect de-skilling. And here are a set of conditions where you should expect roughly the opposite. And it so turns out JointBot is that kind of organization. It's one of 8 startups in our sample that was building robots to pick and pack goods. It was founded on the premise that workers would initially control the robot directly to do the work, and that over time they would learn from the worker so that the robot would become more and more autonomous. We have data covering 3 phases of their work, going from prototyping through scaling the solution. a fair amount of field data, actually fair amount, quite a bit. A lot of interviews, a bunch of site visits, and so on. And I was talking with Morgan about this about a year ago. We have a huge glut of data of users interacting with these systems to get the job done, with individual usernames and so on. And we have LinkedIn data. The way to think about what happened at this firm that was special or unusual is you have people who, with the equivalent of a high school education that this firm called drivers, who would, in the beginning, do one-to-one control of a robot to pick up a good and drop it in a bin, right? And initially, this was a VR headset with this really complex controller, and it moved to a mouse and pointer screen because of feedback repetitively levied by these drivers. Their degrees and sort of entry point education and so on are sort of high school or undergrad level, but certainly no technical training and no industry experience. And eventually, their control inputs, much as a Tesla driver provides control inputs to Tesla to help train their auto driving capability, help these engineers and managers and so on do better algorithm design. So, and this is one way to look at the data. This is impossible to digest in this amount of time, so I'm just going to highlight a couple of things. And this is all recorded, so you can go back and look. But here you'll notice these are the phases of effort for this firm. This is the number of orders that the firm processed. This is the number of times a robot handled a good to assemble a customer order. And you'll see one of the conditions for the study here, which is professionals, the engineers and so on, and drivers shared control of these robots throughout the study period. So every single day, an engineer or several would be controlling these robots. That's the gray bars. And the darker bars are these drivers. And you can see the curves cross when the firm starts to scale. So you have many more workers. At the peak employment for these drivers, it started at 1 and went to 33. Total number of individuals, about 41, 42. And they started to crank in automation as these driver inputs allowed for that capability to become more and more automated. But the point is, professionals and drivers were doing this job throughout the firm cycle every day together. And they ended up resolving problems around the design and implementation of this product together as well. So I'm just listing a few here. I can only share a very limited amount of data in this amount of time. But I'll give you one instance of a problem that was solved and the skill that these drivers built in helping to solve and identify and solve this problem, actually. But there were numerous. These are all existential to the product's success in the market. And we have data on these drivers' involvement in solving these problems. You'll notice none of these are our ML code had a bug. So they're not touching the sort of beating heart that engineers might traditionally be protective of. But here's data from one of these drivers this is a dead giveaway. This is a person who started with a high school diploma and by the end of the study period was an engineer by title in the organization, had no engineering degree. So as a driver, you start seeing failures where, for example, the part that attaches to the grip of the arm starts to break off and we don't know why. And drivers can point out, oh, well, it's sweeping across the bin and hitting other items. And we don't see that. Then we can, on the mechanical side, look at this load analysis and be like, all right, yeah, this part of the flange or the connecting point is a little weak. Or the AI motion side be like, OK, when we pick the item, let's pull out better and then up to the next routine. So engineers were gathering their data, so to speak, to engineer their better product through collateral sort of vicarious interaction with these drivers in the beginning. And it led to some skill for these folks and improved technology. So for instance, these non-professionals were learning about things like control for robotics control, but also what is a UX and how do you build a good UX, right? I'm going to keep going fast here because I have only a few minutes left. Problem solving. So in the next phase where we're revising the solution, the robots were not producing at a level that their customers would like. This is how these folks would help. So professionals prioritized throughput solutions based on driver feedback. So drivers were becoming more proactive. This is a driver who said when the arm stowed an item, it would only go back to this one waypoint in the space. We were like, is there potential to create more waypoints so you could move take less time to do your move. And they said, yeah, we put them on the back burner. You're sure you want to bring that up? And me and the other driver looked at each other like, yeah, just enable it and we'll test it. And we did, and it improved. We went from 100 to 250 units per hour, or UPH, just based on that. So that factor improvement came directly from a driver suggestion. This became relatively typical at this point. And they started to, I'm going to just summarize, answering customer support calls at weird hours of the night. And some of them started to like to do that. And then angled for a title, which was product support specialist. And they got it because that was practically what they were doing. The formal recognition of that skill vis-a-vis a title change came later in the data set, but they started to do it because nobody else was available. They, again, were developing more complex skill here. Again, none of it touched the ML code, and this added to features and sort of accelerated progress to product market fit. Last bit that I will mention is that they started a Central American operation once they achieved product market fit. And that's where most of the drivers moved, and these dynamics attenuated rather significantly. So the product was sort of settled, and these drivers now had less of an opportunity to contribute in this way. They still had the same amount of slack time, but what they could do is contribute to mechanical opportunities because the firm was insourcing manufacture of their own robots in that Central American facility. So instead of now digital contributions, these turned to mechanical contributions. And the workers, again, were just sort of mixed in across these boundaries. So it was easy to pull a driver into the mechanical team, and these drivers would learn about mechatronics and manufacturing optimization and so on. Here's the LinkedIn data just to give you the sort of more records-based evidence. We have a representative sample of these drivers across the entire period on LinkedIn. 76% of them advanced into professional level jobs, 9 outside the firm, so that's 42%. And 4 of them, like one of the people that you saw, was without a new engineering degree or certification, moved into jobs that are typically would require that. And we have qualitative data that corroborates for those who were not on LinkedIn that this is roughly the dynamic. And so I think what we don't have are enough stories about how things can go right in work with technology. This, I would put it to you, is a pretty rare set of conditions. You have a near ideal, sort of exaggerated case in order to see how could things go right with respect to non-professional skill development in the development of technology. It's not ideal, but certainly allows for some insight in this territory we tend not to look as researchers, I think. And so there's some key mechanisms here: shared performance of a core production task, proactive engagement via slack time. Slack time was really important. And the more complexity there is, the more uncertainty there is in the tech, the richer the opportunity for that person who's also engaged in these conditions. That's it. Thank you very much. Oh, we have Q&A. Sure. Or not.
Hey, Matt. So you're detailing the interaction between high skill and low skill workers in these robot manufacturing companies, and I'm wondering what you think if you had to extrapolate to other parts of the economy, maybe LLMs. For me, it seems related to one of the results Ethan showed. He said there's no bad lawyers anymore. So I'm wondering if you could sort of look for these sort of dynamics elsewhere.
Yeah. So. That's the wrong question to ask somebody who's obsessed with how things could go right, because of course my generalizations are not they're probably excessive. So I'll just say, here's what I think. If you were to have these mechanisms consistently available to a workforce that otherwise is disadvantaged with respect to their value-added skill, we should expect roughly comparable results. Could these conditions obtain inside a large bureaucratic, well-established multinational corporation? Study required, but it seems possible to me. I've presented these findings to corporate audiences a couple times now, and they say, oh yeah, no, there are places inside our organization where we're developing new product, for instance, where this could be done more or so deliberately. Have engineers and these people doing some form of direct mediation of the control, the sort of output function of the firm, have them cohabitate. Engineers know that people who are in the loop in that way can see things that they don't. The engineers were not, I have no data, we collected no data that indicated engineers were somehow resistant or rejected this kind of help. They sought it out, never on the ML code. So in principle, I think if those mechanisms show up, we should expect these kind of effects.
Great, thank you very much.
Okay, thank you all. And thanks to the organizers for inviting me to share this paper with you all. They haven't shared to the screen yet? Okay, great. I'll just get going. I'm Alex Mooring. I'm a PhD student at MIT, and I'm super excited to share my project with you all. That is joint work with Nikhil and Tobias, also at MIT, and then Pranav Rajprakash, who's at Harvard Medical School. So this paper is called Combining Human Expertise with AI, Experimental Evidence from Radiology. So let's dive on in. So to start, I want to notice that AI is probably not too big of a surprise to us in the room, is a transformative technology. It's general purpose, affecting many different tasks and jobs. And one thing that's kind of unique about AI is that it is particularly influential at impacting tasks that have traditionally been reserved to high-skilled labor. And so radiology is an iconic example of this. Radiologists are very high-skilled, very, very highly compensated, something we also learned the hard way throughout this experiment. But AI has made vast inroads in automating tasks that have traditionally been done only by human radiologists. So in particular, computer vision has made vast strides, and some of these computer vision models are quite good at reading chest x-rays now. So here's a famous quote by Jeffrey Hinton saying that it's completely obvious that we should stop training radiologists now. This was, you'll notice the date, it's 2016. This didn't turn out to be the case. So we think this is sort of evidence that at least in the medium run, humans are going to be working alongside and collaborating with AI. And so we think this is an important thing to study. So I want to further motivate this paper by highlighting a few things that humans are good at relative to the AI, or something that they can add, as well as some potential weaknesses that humans may bring to the table. So first, humans have access to a lot of private information in many settings. In the case of radiology, this will include the patient's clinical history, notes from the referring physician. These things are not yet encoded into the training data, and so they're not included in some of these AI algorithms. And so this information may be valuable in terms of correctly diagnosing patient cases. On the other hand, humans make mistakes. They may not optimally combine their own information with that of the image. And so, this is something that AI may excel at relative to humans. And then finally, humans are quite expensive. So radiologists are highly compensated, and their time is very, very expensive, while we can run inference on some of these algorithms quite cheaply. So we're going to try and address these three related research questions in this study. First, we are going to ask how valuable is contextual information in an AI assistant in improving human diagnostic accuracy. So to do this, we will conduct an information experiment. We'll recruit radiologists to read chest x-rays, and we'll randomize whether or not they have access to a patient's clinical history, as well as an AI support tool that I'll tell you more about in a little bit. Second, we will try and understand how humans combine their own information with that of the AI. And so what we'll do is we'll estimate a model of human belief updating, where we allow for deviations from Bayesian updating. Okay, and we'll try and understand what biases humans exhibit and how this impacts the design of human-AI collaboration. So what I mean by that is we will take the view of the social planner, and we'll solve the optimal delegation policy, where we can, given a case, we can decide whether or not this case should be read by a human alone, a human with access to AI, or fully automate the case. And so with that, I will now very quickly tell you about the experiment we run. I'll share some treatment effect estimates, and then I will quickly explain how we estimate a model of belief updating that allows for biases, and how this informs the optimal delegation problem. So in this experiment, we will recruit radiologists to our platform. We designed this platform to, as closely as possible, mimic clinical practice. So radiologists will read chest x-rays, and then the largest deviation from clinical practice is that rather than asking radiologists to enter a free text report, they will enter structured data on the likelihood that a pathology is present. So we'll collect probability assessments for about 100 pathologies, and we try and structure this in such a way that it's time efficient, so they're not actually entering 100 sliders on each page, and you only enter a probability for a child pathology if the parent's present, et cetera. And so, I just want to highlight this as the main deviation from clinical practice. What will we vary? We will randomize whether humans have access to an AI algorithm. This is a computer vision algorithm. It's called the CheckSpurt algorithm. And what this does is, using only the X-ray image, it'll predict the likelihood that 14 pathologies are present in a chest X-ray. In the paper that developed this algorithm, they show that the performance matches that of 5 board-certified Stanford radiologists. In our sample, it actually exceeds the performance of most humans, so it seems to be a pretty good algorithm. Second, we will cross-randomize whether or not humans have access to contextual information. This will include things like the patient's labs, their vitals, but importantly, this will also include a patient's indication, which is the written note from the referring physician saying, look for pneumonia in this case, for example. So this, potentially contains a lot of information that the humans could use. So what do we find? Here I'm showing the treatment effect, where the outcome is the deviation in a radiologist's assessment from that of a diagnostic standard, where the diagnostic standard for every case is created by aggregating the opinions of 5 board-certified radiologists from Mount Sinai. What we'll notice is that, looking at this point on the left, having access to AI doesn't really affect the accuracy of radiologist assessments. Clinical history, on the other hand, does lead to a slight improvement. So negative here means you're moving closer to the diagnostic standard, becoming more accurate. So there is some value in this private information that radiologists have. And of course, there's no interaction effect over here on the right. Now, this is somewhat of a puzzle. I told you that this AI is pretty good, better than most radiologists in our sample, yet we're not finding any treatment effect of AI. And so, why might this be the case? One hypothesis is that radiologists are just totally ignoring the AI. We actually find that's not the case. So here I'm showing the treatment effect of the deviation of a radiologist's assessment with that of the AI. And in cases where the AI is available, radiologists are moving much closer to the AI's assessment. So this is maybe a little bit more puzzling. They're moving closer to the AI. The AI is better than most radiologists. Why aren't we seeing a treatment effect on average? And we sort of spend the rest of the paper trying to unpack this potential puzzle. Here's what I think is sort of the main, at least reduced form result in the paper, where I'm showing the heterogeneous treatment effect of having access to AI on diagnostic accuracy by the AI's reported signal. So the x-axis is, whether or not an AI says something is not present, it's 0 to 0.2, or something is definitely present over here on the right. And what we see is there's this sort of inverse V shape in the treatment effects. And so what I mean by that is, on the left here, if the AI says, pathology is definitely not present, humans are actually getting better when they have access to the AI. On the right, we have fewer cases, so it's a little bit noisier. But in the middle, when the AI is uncertain, we have pretty robust evidence that humans are actually getting worse when they have access to the AI. So this is kind of the first evidence that humans are not Bayesians. Bayesian, on average, should never become less accurate when they have access to more information. And so then we try and further unpack this sort of interesting pattern in the rest of the paper. And so to do this, we estimate a model of belief updating where we allow for biases where humans can deviate from Bayesian updating, and we allow for 2 different types of biases. First, we allow for humans to over or underweight the AI's information relative to their own information, and we'll call this automation bias or neglect. Second, we allow for humans to not correctly account for the statistical dependence between their own signal and that of the AI when updating their beliefs. So for example, we might think that humans treat the AI's information as independent of their own conditional on-the-ground truth. We'll call this signal dependence neglect. We test this empirically. We find evidence of 2 biases. The first is automation neglect, so humans are not responding enough to the AI signal. And the second is going to be signal dependence neglect. So humans do treat the AI information as independent of their own conditional on-the-ground truth, even though this is not the case in the data. And interestingly, the model that we select matches this sort of inverse V shape in heterogeneous treatment effects. So these biases can explain this fact that we found where humans are getting worse when they have or when they receive an uncertain AI signal. So the upshot of this analysis is that despite there being large potential gains from optimally combining the human information with the AI signal, the biases humans exhibit lead us to fail to capture on these gains. So now I want to talk about an optimal delegation problem and how these biases impact the design of human-AI collaboration. So in this exercise, we are going to imagine we're a social planner who observes a case. We observe the AI assessment for free, and then we want to decide whether or not this case is to be read by the human alone, the human with access to AI, or fully automate the case. So in particular, we're going to minimize this loss function where V is going to be the expected decision loss on a case in units of false negatives. M is going to be the social cost of a false negative. Importantly, M is not observed in our experiment, so we'll just show the solution for a range of values for M, and then we'll also weigh this against the dollar cost of radiologist time, which we can estimate in our experiment. Here's the results of the delegation exercise, and I will do this both for a Bayesian human who's optimally combining the AI information with their own, as well as for the humans in our experiment. So first, let's focus on the Bayesian solution. What we'll notice is on the x-axis here, I'm plotting the social cost of a false negative. This is the term in that loss function that we don't know, so this is just for a range of values. The y-axis here is going to be the share of cases that are assigned to each modality. And what we'll notice is that as we increase the social cost of a false negative, for a Bayesian, we have more and more cases being read by human with access to the AI system. And this is because they're optimally combining the information. The only reason we might not want to give a human the AI or if they're acting as Bayesians is because humans take slightly longer when they have access to the AI. But we see that's very rarely the case. Looking at the humans in our experiment, things look quite different. What we'll notice as we increase the social cost of a false negative, we're seeing more and more cases being read by a human without access to the AI. And the intuition for this is quite straightforward. And you can think back to this sort of inverse V graph I showed you earlier. On cases where the AI is quite confident, it's already doing quite well. So despite humans getting better when they have access to the AI on these cases, we just want to save on the human effort cost and fully automate those cases because the human's already doing well. On cases where the AI is uncertain, this is where the human signal is most valuable. However, we notice that humans actually get worse when they have access to the AI in these situations. So we want to assign those cases to be read by the humans without access to the AI. So this is why we have this bang-bang solution where a case is either going to be read by a human or the AI, but very rarely the human with access to the AI. So I'm running out of time, so I'll briefly wrap up now. Our objective here was to try and understand how we can design human-AI collaboration in a radiology setting. 3 things I hope you take away from this talk. First, on average, AI doesn't seem to improve the assessments of radiologists. Second, and this is what explains this first point, is this is because humans exhibit biases. This is not new, but these are important biases. I'll just quickly wrap up. Sorry. Humans exhibit automation bias and signal dependence neglect, and the result here is that AI can hurt human performance when it gives an uncertain signal. The upshot of this is we find that AI-assisted humans are rarely optimal, and that it seems most likely in such settings, humans are going to be working alongside AI rather than collaborating with AI and the optimal solution. So thank you for the time. Happy to take any questions.
Great. So when following domain expert doesn't capture expertise, so this study I've done with the division Arvind, they are sitting down there, and we are from the Department of Management Science Engineering at Stanford. So we started from the fact that a lot of firms are investing in AI, right? I mean, this conference is about this, but not all of them are seeing return on investments. And a lot of the research that I've seen here so far has been focusing on why this doesn't happen, looking at the human-machine interaction. Humans have biases, right, when we interact with AI. So here we are taking a different approach, and we are trying to see what happens upstream in the development process, right? And specifically in a moment where AI developers try to elicit domain expertise from experts, right? So think about, you have to design an HR development, an HR tool for HRs, right? You want to understand how the HR process works, that you need that kind of domain expertise. And AI developers usually don't have that kind of expertise, so they need to go on the field and try to understand who are designing the tool for, right? The interesting stuff is that oftentimes, if you think about companies, and if you think about the hierarchies among which companies are structured, domain expert doesn't have the authorities for eliciting those expertise, right? Think about, for example, a sustainable manager that is hired in a company and needs to go in a purchasing department and convincing people to give him time because he wants to help them making more sustainable buying decision. But these people report to another structure. They have another boss, like another kind of boss, right? So it's very difficult to go there and convince them to give you time. You don't have the authorities for imposing sanctions, for example, or issue orders, right? So how and under what conditions professionals, and we will focus on AI developers specifically, they don't have formal authority over domain experts, are able to elicit expertise, right? So that's the kind of question that we ask ourselves here. So I think it doesn't work, so let me, because there is a Zoom meeting there. There we go. I fixed it. So to answer this research question, we draw data that comes from long collaboration with a big fashion company that we call Wait, like this for maintaining the anonymity. We've been working for 4 years with this company, and we have participated into meeting with the head of data science, and we have data about like all the things that they have done. We have access to their information, their technical process maps, and we have been able to talk and observe how the stakeholders they were dealing with were actually reacting to their developments. The interesting stuff is that we found that there were, among the different projects we observed them working on, there were two that we were interested in. Because they were kind of very similar projects. They had like the same team of AI developers, of course talking with different domain expertise. And the first one was a project that aimed at, the goal was let's try to improve the way we distribute products across the supply chain. So we allocate products across the supply chain. The second one was more about, can we improve the way store managers schedule the workforce? So can ask people to come to work in which day? And we were interested in these two projects because, well, the first one was a kind of success, right? So basically, the data science team was able to develop a tool, roll it out. They had positive results. In the second case, the elicitation of the expertise was not successful, was ineffective. And so we asked ourselves why this happened, right? In similar contexts, two projects, the same team had completely different results in eliciting expertise. And what we found is that this part here is interesting. So there's a kind of interplay between the task and organizational structure that affects the way AI developers are able to elicit expertise from domain experts. So let me walk you through the model that we developed for explaining what happened. So first thing, if you look at the center here, in both projects, the elicitation of domain expertise happened in two different steps. So in the first one, they had to access domain experts, right? So identifying who were the domain experts in the company to talk with that had the domain expertise they needed. And then the second step was eliciting the domain expertise, so collecting domain expertise with them. So experts and expertise, right? So what happened is that in the first project, experts were clearly eligible. So it was easy to identify them and connect with them. While in the second one, experts were kind of illegible, hidden in due to the interplay between the organizational structure and task structure. About the elicitation of domain expertise, we'll find another additional difference, which is that in the first project, expertise was concentrated in the hand of domain experts. So talking with one expert was enough, because that expert had all the expertise they needed for understanding what tool to develop. While in the second project, expertise was diffused, right? So everyone had a kind of piece of expertise that was useful, but it was a puzzle, like trying to synthesize all of them. So what I'm going to do right now, since like there are a lot of evidence in the paper, what I'm trying to do right now is just to give you one evidence for why there's a differences in access experts were eligible or illegible, and one evidence for telling you why expertise were either concentrated or diffused, right? That's what I'm trying to do. Okay, let's start with the first one. So I will talk about why single versus multiple line of authorities makes expert legible versus illegible. So the story of the first project was pretty straightforward. the idea was, how do we improve the way we distribute products across supply chain? So the team of developers went to the head of supply chain that had a kind of overall view of how the supply chain was organized and said, there's a small team that is led by the head of allocation, made of 9 people, that actually takes this decision. So the head of allocation had a clear capability to broker the connection with all the 9 allocators, so the developers were able to access them, spend time with them. They had this kind of temporal authority over them for collecting data. And that's a kind of single line of authority that you don't see in the second project, right? So in the second project, the idea was, how can we improve the way we schedule workforce in the stores, right? So clearly, they went to the retail finance and had all the sales and cost data, right? And they said, like, you should talk with the store managers, right? And there were 200, but reporting to like different district manager and regional manager, and then where they were reporting to the head of operations. So clearly here, what you see is that there are kind of multiple line of authorities for accessing the store managers on the field, right? So this complicates the legibility of domain experts, right? The access to domain experts was complicated by the presence of single or multiple line of authority rather than single. Let me give you an example instead for the second part. So why expertise was concentrated rather than diffused, right? So let me talk about like clear versus ambiguous jurisdiction. In the first project, there was a kind of clear jurisdiction over the task. That means that the groups of allocators AI developers were talking with had a kind of authority to speak about how the task should have been done, right? Because they had control over the turf, like or control over the task. They said, like, this is the way tasks should have been done, right? And it was easy to understand how it should have been done because there was a kind of unique perspective on the field, right? When it comes to the second project instead, they were kind of, you remember the kind of organizational structure I showed you, there were multiple occupations involved. And every occupation had a kind of different view on how the task should be enacted. So, if you think about retail finance, I told you they have this kind of perspective about optimizing cost and revenue. Well, if you have the store manager and you ask them what are like a good scheduling of the workforce should look like, they say like, it's about like retaining the key employees, right? Because I have some 3 or 4 employees, they can do whatever they want. They can show up at work or not, but when they are here, they sell a lot. So it's kind of, everybody had a kind of different perspective. And so this complicated the synthesis of expertise, and it makes diffuse in the second case rather than concentrate in the hand of allocators that they had a clear jurisdiction over the task. So what is the outcome of all of this? That the first project, the same AI developer team had a clear representation of the problem. They knew what should have been done, right? And they were able to converge with just one single valid option on the table. Let's improve the forecast of sales in store. That will help allocators making a better job. How can we help in the second case store managers making a better job? Was unclear. Everybody had a different expertise, was diffused. Everybody had a different vision how to do that. And they had multiple and attractive options on the table, and were not really able to converge towards a solution. Then we call this an effective versus ineffective elicitation of expertise. So we developed a theoretical model here for answering our research question: how and under what condition professionals are unable, without authority over domain expert, are able or unable to elicit expertise. Right? That's the kind of main contribution we have here. Second, it's important for us, and think about if we haven't done that, how it was difficult to like tell about the evidence that we have, or represent the evidence that we have here, dividing expert and expertise that we draw from the sociology literature here. Expert and expertise are 2 different things. Expertise can be concentrated in the end of domain experts, or not, can be diffused, right? That's the second takeaway of this presentation. The last one, and we try to make a contribution. We started this presentation talking about why some AI projects fail. And yeah, of course it can happen that humans have cognitive bias, right, in the field. But there are things that happen before in the development process that can affect later on. I mean, this is kind of evident, it was evident also in your presentation, right? And so task and organizational structure, in this case, affected the capability of domain expert to elicit expertise. And that's a third contribution. task and organizational structures are not just background conditions, right? They are not just there, and we can like isolate humans in the vacuum and study them in lab experiments. Of course, it's useful. It's useful. But in the wild of organization, there are a lot of interacting spillover effects that come from task and organizational structure that needs to be controlled for, right? And so that could determine also why some project could fail. Thank you.
We have time for some questions from Luca, or actually one of the other speakers did. So.
I have a question for Luca. So I'm wondering, have you considered it's related to the project characteristics? The first is about product allocation,
Yeah.
and the second is the workforce scheduling.
Yeah.
So the politics may happen, and then the store managers and workers may have resistance over this scheduling. Could that be one of the causes of the project failure?
Yes and no. So, I mean, yes, it could be later on. But we were focusing in the development process when the tool was not already conceived, right? So there was just, let me understand your expertise. That was a stage, right? They were not like thinking about how to replace them. And in both cases, we could have seen like instances of people fearing that their job could have been replaced. Also, locators could have had the same problem, right? So I don't see a difference in the two cases about like the fear of being replaced. We'll see that the outcome actually at the end was like, since AI was developed in the first case and was rolled out effectively because of the elicitation of expertise, kind of people lost some power in their organizations. I would say like that in a diplomatic way, but I actually don't see that. I mean, it could happen, but not in this case.
Any questions for Luca or
Just a comment, suggestion on the question. User involvement of technology in what technology takes the power to involve the user in the creation of technology. There's a success. It looks like in your two experiments, two cases, one supply chain was much closer to the decision makers who are using the technology, and they are two quite involved in that. Whereas the store management will be quite far off in terms of their involvement, and you have 200 stores or so. That could be one of the explanations.
And we demonstrated that's important, right? So the kind of organizational structure in which this kind of elicitation of expertise takes place determines also the fact that you are able or unable to elicit expertise. So that's kind of what we try to demonstrate. Yeah.
any questions for Luca or one of the other speakers?
Because when you took the boss out of the equation, did you get any better results?
So sorry again?
You took the boss, the authority figure, out of the equation. Did you get any better results?
We don't have that kind of condition, but we specifically focus on that, right? So we don't have like the counterfactual when you have like, the authority over the main experts. We don't have that.